Today we are going to present our independent research to scope and understand the use of artificial intelligence in cartographic design and decision making. So I would like to talk about basically the idea of Carto AI. Basically, the idea is to improve the decision making. People might often ask, like, what do you mean by whenever you are telling the decision making in cartographic design? I would speak more towards the end of the presentation. So here, when I'm talking about cartographic design, I'm specifically talking about cartographic generalization. And why cartographic generalization? I would answer this question in a while. And how are we going to do it? So we are going to do it by using artificial intelligence techniques like artificial neural networks and also some kind of machine learning methods. So how are we going to integrate this kind of advancements into cartographic design? And I would like to present a little bit of backstory, how it all started and how it kept me thinking towards this point where I am presenting our independent research. So this is a map of Florida. This is my first ever cartographic map. You can see that it's pretty gaudy. The line work is not so good. And you can see there are, anybody from cartographic design, the professors or the students can say that it's a bad map. It's not looking good. It contains a lot of generalization that has to be done. But how are we getting decided like it is a bad map? So we are visually examining it. Is there any quantification for it? So these were few questions that I had in my mind. And this is my first ever cartographic map for 370 at University of Wisconsin-Madison. And I've lost a lot of points for bad generalization. You can see that it's, so I lost too many points. And Alicia Iverson was our TA when I was doing this. And I was asking her, like, what is a good generalization? How can I quantify a good generalization? Okay, I'm new to cartography. This is my first course, and how could I do this exactly? You can see that there are a lot of comments around the line work and line styling, which I wasn't sure at that point because cartographic generalization was new. And for somebody who is interested in designing things or making maps, this is a very hard task to decide what generalization is apt for this specific map. So that's where the fundamental idea started. I made a resubmission back then, and now it's looking much better than the previous map I have already shown. And you can see the line work is more generalized, and I've gained few points back then, and I was able to make a good score. And you can see I've removed the Key West Islands, and which I didn't know, like, to do this particular decision making. In order to do this, it is very difficult in terms of cartographic design. Why? Because there is no informed or well-informed answers from the research perspective to tell what is a good generalization in a way that can be quantifiable. So if I mean, so I just showed you two maps. You can tell that, but after seeing this particular map, you can tell that this is a good map, this is a better map, which has good line styling, maybe the color scheme, or it is looking much visual, the visual accenting is improved from the previous map. But how can we tell a machine, like, this is a good map, and that was a bad map? So this kept me thinking, and that's how I've tried to understand the major problems in the cartographic design. And cartographic design is a very broad subject, and in that broad umbrella, I'm going to pick up these few problems which that kept me thinking. And the first one is cartographic generalization itself. So when I'm talking about cartographic generalization, whenever you are generalizing the shape, for instance, this is a map of Wisconsin, and you can see that there is a non-generalized and a generalized versions of it. And the generalized version, whenever you see the generalized version here, you can clearly tell that, okay, this has been generalized, but how much control did you have when you generalized this? Like, did you had control over the points? No, I think. So when we go to Map Shaper, we just give a percentage, and we don't have any actual control over the points that form the shape. So this is the first problem that I have seen. And the second problem is the subjective experience of generalization. And you can see these both are generalized map of Wisconsin. How many of you feel that the map towards the right is correct generalization? May raise your hands. Okay. How many of you feel that left map is more generalized and correct? Okay. So we do have like answers for both, like for including apostille islands at the top. So what's the logic behind it? Like we feel if we are connected, I'm from India, I don't know nothing about Wisconsin, I don't know nothing about apostille islands, I might remove it, right? So this is the problem with the subjectivity of the particular generalization. And talking about undergeneralized versus overgeneralized, you can see that this is overgeneralized, and a lot of features are removed. I can tell it after taking the cartographic course. But before taking it, where is the exact midpoint between overgeneralized versus undergeneralized? How could you quantify this generalization? So this is the other problem. And the last problem is the generalization at scale. So zoom is very important aspect. So as we are moving towards more tile-based schemas using multi-tile imagery or multi-tile vector packages, so this is a kind of problem, like how are we generalizing it exactly? Is the generalization correct for the particular scale? So all of these combined, we are trying to answer it in a kind of implementation by doing some kind of approach to making a machine learn what is a good generalization. So in this, the workflow we have adopted is, we took a non-generalized shapefile, just like Wisconsin, and we generalized it using Visualingham and Wyatt algorithm. Then we created a detailed set of labels for every single point that is in the polygon, and we fed it into a machine learning model. We made the model to predict some of the outputs for other states, which we did not train. And we created a concave hull. And from the non-generalized shapefile, I would like to give it to Professor Rob, because we didn't know that there was an algorithm that actually evaluates this particular kind of models, which is a Topfer algorithm, which my colleague would explain in a while. And we created a concave hull. Now we did a visual examination to make sure. So because machine learning can create junk outputs, which we cannot even realize. So evaluation is very key, very important as AI is evolving more and more. So the outputs has to be evaluated in a certain way. And so this would be the concave hull. Now we do the visual examination. So this is divided into 3 phases. The first phase would be feature extraction and label creation. Second phase would be training and label prediction. And the third would be the evaluation phase. So this would be done in 3 sets. And I would talk briefly about the implementation. What is the basis? Why did we choose Visualingham and Wyatt or Douglas Packer for this? So Douglas Packer creates spiky lines. Even after removing 95% of the points, we can retain the shape. So that's why we have used this particular algorithm. And the example which I have shown is like it would hold the largest triangle. As you can see, the smaller triangles are removed in each stage. And this is taken from Mike Bostock tutorial. And for the second part, like after taking the non-generalized shapefile and taking and creating a generalized version, we adopted Visualingham and Wyatt, and we have seen that a certain kind of visual examination, and we felt that this would be a correct kind of generalization for the training. Then we fed and we created the labels, which would be explained by my colleague.
Thanks, Sid. So initially what we have tried is we just took latitude and longitude for a state and the labels that have been generated by Visualingham and Wyatt. And when we gave it to neural networks, it was unable to predict anything. It just said no for all the million data points for Wisconsin. So then we realized that, okay, just having a latitude and longitude might not be enough for a machine learning model to understand how the geography or the geometry of the state looks like. So we went back and created a set of manual features for every latitude and longitude with the hope that they capture some local geometry of a state. These are some of the features that we have, where by taking the couple of points on the lat long, we computed the lengths, angles, and a few ratios. Okay, but still there is a problem of curse of class imbalance, a standard one in machine learning, where generally people expect when we say machine learning can solve, it's not a magic that it can do. As in, we can't really expect a machine learning model to detect a needle in a huge haystack. So the same way, in our data, we have around 1 million data points for a state. And as Sid explained earlier, 95% of the data points can be removed and still good visualization of the state can be achieved, which means in our data, we have no, we have no as the label for around 95% of the data, and only 5% of the data has yes. So when we just feed this directly to a model, a dumb model can just say no and still achieve 95% accuracy because it's correct 95% of the time. So it tries to learn just to spit out no, but that's not what we are expecting. So a workaround that we came is we tried to use a weighted random sampler, which basically means the number of times it sees yes is consistently same as the number of times it sees no. Okay, but still we have another problem before giving it to a model, which is about feature scale mismatch. So suppose I take the map of Florida and California. They have different scales of latitude and longitude. Their shapes are different, which means the features that we computed will be widely different. If it is at the same state as well, suppose let's consider only Florida, the different features that we compute has different scales. So a workaround is to use feature some kind of normalization or standardization before we give this to a model. So we implemented two kinds of machine learning models. One is the standard vanilla-based artificial neural networks, and the other one is a decision trees, which we sort of plan to use it as a baseline, where the decision trees are sort of interpretable because we can understand the rules on how it is looking at the data and trying to classify. And our hope on using artificial neural networks is to capture the nonlinearities in the entire huge chunk of data. And the input will be all the features that we have constructed, and the output will be basically an yes or no for each lat long. Before looking at the outputs and evaluations, I would like to first explain a bit on the limitations part. So the first and foremost limitation is we are losing the inductive bias on the spatial context because we are removing all the points and we are placing it in a CSV file, which means that we are losing how they spatially look. Yes, we did manually construct features in the hope that they represent some local geometry, but we want machine to understand instead of we manually constructing. So the workaround is to use a sort of advanced neural networks called GNNs, graph neural networks. The name suggests it has some graph component in it, which looks at all the points together and tries to come up with which points are needed and which points are not. And the other big issue that we have currently as well is the lack of oracle ground truths. So as Sid was mentioning previously, so no one can really say which points are needed for a good generalization other than few critical points. Suppose it is at the edge of a state, yes, that point might be needed, but if it is just at a straight line, I can choose one point, Sid can choose another point, and we both will still arrive at the same visual looking map. So this lack of oracle ground truth creates multiple feasible solutions, which looks visually same, but still the solutions are different. And it also makes the quantitative analysis difficult because the standard metrics like accuracy or precision or recall will definitely fail. So a workaround, as Rob has suggested, is to use Topfer's radical law for visual evaluation. So in a nutshell, Topfer's radical law states that we can simplify maps by removing less important objects while retaining the most important ones. So the original law in the 60s, it just has a formula which says how many features we need to achieve a particular visually looking one. And re-implementation of that in the cited paper has described in more detail on how to generalize, how if we have a feature, we can get Topfer's level, different levels of generalization by using this Topfer's law. Here we take the map of Idaho. The left one is the original source map, and we just take a feature, the forward length, and when we just when we just use Topfer's law at different levels, we sort of get a good generalization as we go across. We lose features, and we can just sort of understand, okay, this is Idaho. Okay, I would like to discuss a bit on the result side. On the top, you can see Texas, and on the bottom, you can see Florida. And the first three correspond to the three levels of generalization using Topfer's law, and the right two correspond to the neural network and the decision tree generalization outputs. Few things we would like to point out is, if you see the neural network and the decision tree outputs are quite close to level 2. In fact, in the case of Florida, it's actually quite better because it still was able to preserve this. In the level 2, it lost that ability to preserve viewpoints, but in decision trees and neural networks, we are able to still preserve it. And we are able to achieve a quite good compression ratio. In case of decision trees, it's around 99%. This also leaves a few limitations on Topfer's radical law because it can lose important details while we are trying to construct the concave hull. In our case, we implemented Topfer's law by using forward length. This is a visualization of the state main, where if you see just at the level 2 itself, it lost some critical details, and because of which we can't really say this might be the best way we can evaluate an algorithm. So we can't say that a machine learning model did not learn just because it doesn't look at like a level 2, because that's not main. So we actually have some open questions on our side. Feel free to reach out to us if you have any ideas on implementing better features or modeling part, and more. And the most important one is if you have any thoughts on how to evaluate the model. With this, we would like to conclude, and I'm sorry, we'd like to conclude and give credits to our collaborators, Ramakrishna, who is here, and our advisor, Frederick Sala. And we would like to acknowledge Yuha and Rob, who are at the geography department and who gave constructive feedback during the project. Thank you.
We have time for one question, but I'm gonna use my privilege to ask it. And maybe it's just more of a comment than a question. No, it's actually just, have you guys looked into the idea of persistent homology and how shapes bend in data space? It's from topological data analysis, and I think it would get at some of what you're trying to get at with Topfer. But if you're not familiar with it, we can talk about it more later, but I think it might be helpful. Yeah. And with that said, I think we do have time for one more question that's not me.